Okay. All right. Thank you, everybody, for being here today. My name is Kyle Nielsen, and I'm part of this group. If everyone would like to stand up from our class, and we'll briefly introduce ourselves and say our names. I'll start over here with Daniel.
I'm Dan Jarman.
I'm Grace Alabaster.
George Carroll. I'm Owen Carnes. Rick Schauber.
Robert Staub.
Trick Wami.
Todd DeReese.
Thank you, guys. All right. So we have named ourselves Wolfpack Industries, and this is our final presentation today. So a capstone introduction, kind of why are we here? So capstone, a lot of people like to think of it more or less as a senior design project, but it's a 2-semester project. So it began last fall and it's gone through this spring. Overall, the NC State Havelock campus has always worked with FRC East on Cherry Point there to come up with our capstone projects. So basically, FRC East has become our customer, and they have a problem or something that they need an engineering design to be resolved. We as the students form groups, develop a solution for them, and then we have to present the solution to them in a few different stages. And then the customer receives the solution along with our instructors, and they help approve it for us to advance along the way until we have a fully developed design. Why do we do some of these things? It's also part of the ABET accreditation. So the Accreditation Board for Engineering and Technology, they help set up some of the guidelines for us to fill roles and certain things we have to achieve along the way, like fill out documents, establish leadership roles. So we were introduced to the problem by the customer on September 8th in 2022, so last semester. And for us, it was the F-35 was coming out of production and being received by Cherry Point. And they had to do a number of different things to get it up to speed so it could hit the fleet. And what was happening was they had to remove too many components. So it was becoming unstable. There's too much weight in certain areas, and it was in danger of the center of gravity, the CG, shifting so it could potentially fall over in grand scheme of things. The two main conditions would be tip back. So pretty much the aircraft would either be on its landing gear or it would be on jacks and it would rotate at the back axis there where you see the rear tire, and it could tip back onto the rear end, as well as rollover. And then they presented the turnover angle kind of like that to us, which the center tire in the very front, and it could roll to its side and in danger of falling over and potentially injuring the artisans and people who work on it, as well as damaging the aircraft. So like we talked about, for the ABET part of capstone was to establish leadership roles. So we had a few different presentations along the way. We would have team leaders and systems engineers, which would help guide us to each of these metrics for a systems requirement meeting, a concept design, a preliminary design, and a critical design. So we broke up into leadership roles for that. And then we also had an overall project manager who helped keep us on task and act as our main point of contact between the customer to organize communication. That way we didn't have a bunch of different student emails going back and forth and create a potentially messy situation where we've just got random communication all over the place. And just a basic overview, like we talked about, it would be SRR, which advances then to the concept, which then gets more defined into preliminary design, into critical design review, and then today is our final presentation. Daniel.
So we're now going to show our final prototypes. We have a 1/3 scale model of what our wing weight counterweight on this side. And first, we're going to start off with kind of an overview of how it interacts with the aircraft, and then we're going to get a little more specific on how the artisan would interact with the counterweight system. So this aircraft would be in how it's typically presented in maintenance. It's currently on jacks, which is very common. Landing gears may or may not be on the aircraft at this time. In this case, the landing gears are on. But as they're performing maintenance, which you'll hear a little bit more from our software team, as parts are being removed, the aircraft could go unstable. Particularly turnover was the biggest issue that we wanted to address. So we came up with a wing wake design, which is a two-piece system to be placed on the wing. We start out with a light aluminum base, which is light enough for one artisan to place on the aircraft. It attaches to the aircraft, and then using a crane, the main amount of weight, which is a steel plate, is lowered onto the aluminum base plate. We have one for each wing, and that helps stabilize the aircraft from these turnover conditions. So how an artisan would essentially interact with it using this third scale prototype. Once again, can be picked up by one artisan placed on the aircraft. There's then 7 fasteners that go into what is known as the blade seal location. The blade seal is essentially this piece of composite that bridges the gap along the wing from the control surfaces. We can secure it there, and then using a crane, the counterweight would then be raised up, and it would be guided onto the guide post, which have a taper to them. There's also a radius on the bottom of the weight to help guide it along the post, so it sits firmly in place. All right, we're now going to pass it off to the software team to go over their final design.
Hello, everyone. My name is Owen Carnes. I'm responsible for creating the calculator software alongside Grace and George here in the front, which they'll be speaking here shortly. Essentially, the calculator software is made so the engineer or artisan can predict when the aircraft goes unstable into an unstable configuration. And this is due to the aircraft being in a tip back angle, like the tip back angle falls back, or the turnover angle goes unstable as well. So with that, we're going to do a small demo to show you guys essentially how the software works. So initially, the user will be given a calculator application, which we use Python to develop the software. So whenever you open the application, the user will be granted with a user input window. This will allow for the user to put in their basic information that they're given when they receive the aircraft into the hangar. So this will allow them to import their center of gravity locations for every component on the aircraft. So they'll be able to browse and select their Excel file with all those components. In this case, we're gonna do like a demo, so a small sample of those components with you guys. So they're able to store that information into the application. Alongside, they're able to put in their aircraft view now, so whichever aircraft they're gonna work with. For now, I'm just gonna put in a random number. From there, they're able to determine and put in their basic weight and center of gravity of the aircraft. I'm gonna put in some common numbers that would be generally used for that 35B. And whenever they have all their information saved on the screen, they're able to go ahead and press the save button, and they'll be prompted with the saving values window, and it'll go into the main calculator screen. So this interface will allow for the user to look at all their imported parts that you can see in this list box on the top left. Alongside that, they can search by location or by weight for each component that they want to find. So for instance, if they wanted to take off the engine, for example, they could type in engine. And as you can see, they can remove and find that one engine within that list box. And you can also search by weight, as I mentioned. So if you wanted to find components greater than 1,000 pounds, for example, you can type in 1,000, which in this case, since we're only doing a sample, let me do a smaller number. So if we did like 300 pounds, for example, it'll populate all of those components greater than 300 pounds. With that, the user, whatever components they want to remove off the aircraft, they're able to select those components. So in this case, we're going to go ahead and remove the left and right landing gear alongside the engine and components of the horizontal tail assemblies alongside the vertical tail assemblies. So whenever the user selects all of those components, they can go ahead and press uninstall. And as you can see, all those components that I selected get populated into your new uninstalled components list box. These are all the components taken off of the aircraft. And you also can see that we received a new warning sign here that says warning, unstable wing jack configuration. So this means since we removed those components, the wing jacks, if the aircraft is on wing jacks, then those will be unstable and the aircraft will be prompted to turn over in this case. So we're given that warning, so we know it's gonna happen before we actually perform that maintenance. So with that, you can go ahead and add your wing counterweight, which the hardware team demonstrated here a few minutes ago. So you can press the add wing counterweight button and you're prompted with placing a counterweight on the left wing, the right wing, or you can do both at the same time. In this case, I'm gonna go ahead and press both. And with that, you can see that the unstable sign at the bottom left is now in a caution approaching unstable. This means that the aircraft is still stable, but it's still getting close to that unstable range. So just be aware of that, but it's still perfectly acceptable to perform their maintenance. So let's say I went ahead and removed the left and right landing gear and put it back onto the aircraft. You can also see that now that I did that, the wing jacks are displaying in a stable range. So this is values for the turnover angle less than 53 degrees. So this is perfectly acceptable to perform their maintenance. With that, the user can also add artisans onto the aircraft to, let's say if they wanted to place an artisan on the left wing, this would demonstrate them adding the counterweight onto that left wing so they can perform their maintenance. And you can also consider artisans on the right wing. You can place them in any of these preset locations that we displayed here. I just placed them on the wings for now. So with that, whenever the user is totally acceptable and they like all of the components that they went ahead and uninstalled, they can go to the top left of the screen. It's kind of small, but at the very top left, you can hit save or save as. This will allow the user to save all the information that they wanted to remove off the aircraft, which I'm not going to go into too much detail, but they're able to export it to an Excel file so you can save it for a later date alongside importing it back into the program so they can come back to that software at a later date if they wanted to add more components to remove or install. So with that, I'm going to pass it over to Kyle, and he's going to go more into our project approach that we took.
So that was our final design. That was the actual solution to the problem that they had. And if you're sitting here asking yourself, what took almost a year? This is what took almost a year. So the development of the design, SRR, like we talked about, September 8th, the customer came, they identified the problem to us, the gentleman here from FRC East, and said, here's what we've got going on. We need a hardware solution to fix the problem as well as a software solution to identify the problem. So then it was our responsibility to come up with the SRR meeting, which is the Systems Requirements Review. So we had 24 work days that we sat down and we made sure we identified what the customer had said to us. We got a chance to do a site visit where the engineers from FRC East for the F-35 took us around, showed us the facility, showed us the environment that the aircraft is working in, the conditions it goes through. This would be a picture of the actual wing jacks that's attached to it that we're allowed to have. And we got to identify in person what's going on. We've had several site visits since then to help shake down a solution that would work the best. Then we moved on and gave our presentation to them. We broke it into two main sections. Hardware requirements, which were for the physical counterweight that we presented. We came up with 7 requirements, which is pretty much just telling the customer, we heard your problem, we've got a solution, it'll solve your problem, as well as if we follow these requirements, they're kind of the laws and the rules that we followed when set up for ourselves along the way. Software then came up with 10 requirements. And from there, we presented them to the customer, and the customer agreed along with our instructors that we could go ahead and proceed with this and move on into conceptual design.
Thank you, Kyle. So the next phase of the project was concept design. When many people think of engineering, this is the part of it that they think of. Actually starting to get into how are we going to solve their problem? During the requirements part of it, we were identifying what is the problem and how can we solve it. We're now looking at the solution. So to get us started and think about how we would like to solve this problem, we had individual concept review for both hardware and software. So our hardware concepts were all over the place. We had many different designs. We had things from putting a weighted blanket on the back of the aircraft, putting a barbell on the back of the aircraft, to even putting a dummy bomb in the weapons bay. You can see all of these attached very differently interface with the aircraft in many different places and combat both tip back and turnover. But through talking with the customer and through some of our site visits, we were able to narrow our solution down. I'm now going to pass it to George to talk about their individual concept.
So for individual concept, software found that we had two potential solutions to the problem as far as the calculator went. We could either make the calculator using Python, or we could make it in Excel using Visual Basic or VBA. With this in mind, we individually made several different calculators using both programs. And throughout individual concept, comparing these calculators using the different programs gave us some very valuable information moving into group concept, which Daniel will start walking you through hardware's design for that.
Thank you, George. So moving into group concept, you saw our individual concepts. We had many different designs that, as I said, could be located all over the aircraft. Well, as we went for a site visit, like Kyle talked on, discussing with the engineers, we're walking to the back of the aircraft and we're looking at the vertical and horizontals, and they're explaining the process of how the vertical stabilizers are taken off at Cherry Point. And, you know, looking at the space there to work, like, you know, it would be great if there was some sort of work platform that could be placed around these verticals to help facilitate taking them on and off, which our team, willing to take on a challenge, tried to kind of solve two problems at once by using a weighted work platform to be placed on the back of the aircraft. So this was our first design. You can see had some nice areas to walk around and work around the verticals. But if you notice, to accommodate the engine tunnel, that hump that's in the middle of the aircraft, it needed to be really tall, which is a problem because they would have to be working down in a hole. So this idea was put on the back burner. So then we went back to the drawing board. How could we improve upon this? So we made it a lot more low profile to the aircraft. We had some special attachments we wanted to do. But again, looking at it, added some more safety rails. It looks really good, but there's just not quite that much space on the back of the aircraft. Which brought us to what we presented at our concept review, which is a stationary weighted inboard platform and removable outboard platforms that could be attached to help remove the vertical stabilizers. It would be a weighted platform on the inboard section. It would still have all the safety rails to help facilitate removing the verticals and placing them back on. I'm going to hand it back off to George to discuss the software's concept.
So at the beginning of group concept, we developed a logical flowchart as a sort of outline of what the software needs to accomplish in order to successfully address the problem presented to us by FRC. The program needs to start. It needs to accept user input, namely the BUNO, the original CG of the aircraft, and its basic weight. The operator then decides whether or not they are going to remove parts or add parts. The software then does the necessary calculations regarding tip back, turnover angle, reactions, and stability. It outputs whether or not the software is unstable or stable. If it is unstable, you add the counterweight. If it is stable, it is safe to add or remove the parts and continue your maintenance on the aircraft. And then going forward from there, we use the information that we found during individual concept from developing the Excel and Python prototypes to develop formal, well, first, before we did that, we split off into Excel and Python teams. One team focused on developing and researching a formal Excel prototype, and the other team focused on researching and developing a formal Python prototype. And you can see here are some screen grabs from our Excel user interface prototype. And here we have our Python user interface prototype. This is the development of the software as it stood at concept. And using the information from these two prototypes, as well as additional research that we did, talking to programmers, research online, just looking at what various resources were available for both Excel and Python, we found with our requirements, the comparison of what we were able to develop with the same amount of people in the same amount of time for both programs, and the fact that we wanted a very intuitive user interface, we found that Python was the best solution to our problem. And with that in mind, we then proceeded to become familiar with Python programming and proceeded to create the demo that Owen showed you earlier in approximately 6 months. And I'll now be passing it off to Daniel.
Thank you, George. So the next phase of the project we entered was PDR, our preliminary design review. This was probably the most important phase of the project because moving from a concept to an actual design, about 85% of the details needed to be defined before we brought it before the customer and our instructors. And we did that in 52 days. So starting off with the hardware design, what we presented at concept was the weighted inboard platform. Through another site visit, talking with the customer, we found out that the maintenance on that bulkhead we wanted to use on the very rear of the aircraft was being worked on, so it was no longer a viable option. So still wanting to put that weight as far back as we could on the aircraft, we came up with kind of a metal hoop and weight box sort of design to be sitting kind of in the center of the fuselage there. And looking at the frames and the bulkheads that are there, they were not nearly as strong as the original ones we wanted to use on the rear of the aircraft. So that idea was scrapped as well. So what we ended up with was placing weights directly over the jacking points on the wings. So you can see here an isometric view and a top view of the counterweights on the wings. And those counterweights sit directly above where the wing jacks are located, which allows for a reaction directly into the wing jacks themselves. So the jacks remain seated. And you can see from the slide here how low profile that weight really is. It sticks up only about 4 inches off of the wing. So the counterweight system, as you saw from our demonstration, is essentially 2 sub-assemblies. We have the steel weight, which provides the majority of the counterweight, and then a lightweight aluminum base. During our PDR, we had 3 posts originally here in the center, solid posts. And as we moved into CDR, which I would like to point out, that's only 2 weeks. We had to take the feedback from the customer, our instructors, and have 100% of the design done in 2 weeks. So this is what we presented at Critical Design. We went from 3 posts to 2 hollow tapered posts that were slightly taller, 5 inches high, with a 5-degree taper on them to help facilitate the weight being raised and lowered off of the post. The total weight is about 750 pounds, the majority of that coming from the steel weight itself. And the base plate is 3 foot by 26 inches. So it's a very low profile design to put that weight directly over those wing jacks. So you can see, once again, the exploded view of the 2 sub-assemblies of the counterweight and the base plate assembly. And the bolted connections were a very discussed component during both PDR and CDR. Obviously, we did not want our counterweight to damage the aircraft in any way. That's the #1 requirement, right? So as we were discussing this, we needed to find a fastener that would not have any threads in the shear plane. So what exactly does that mean? You can see it a little bit better on the smaller screens. The contrast is a little bit better. But these red and blue components on the bottom, that is the aircraft. The spar is a structural component inside the wing. So we absolutely did not want to damage that with the threads of our fastener. And then the nut plate had the internal threads that we were going to be able to engage with and actually tighten our counterweight down to the aircraft. You've heard us mention the blade seal. We had rubber underneath the aluminum base plate, as well as some rubber to help bridge that gap in between the spar and that aluminum plate, to kind of act as a buffer and to prevent it from damaging the aircraft. And just to show how much detail we had to go into, we had to even account for paint thickness and anodized thickness in order to ensure that we could effectively put the weight onto the guide post and that it would fit properly. I'm now going to hand it over to Grace to discuss software.
So I know we all saw the demo at the very beginning, but at PDR, this is sort of what we had. So it's very similar, but we didn't have as many things in our legends. At this point, we had the search bar, the uninstall, the artisan button, the counterweight button, accurate outputs, and we kind of had an idea of maybe where the stability bounds were. But through communication with our customer, we've realized that those visual sanity checks were very important to them. So we wanted to pursue those stability bounds a little bit further, and we'll show that as we progress. But in terms of just saying, oh, we have accurate outputs, that doesn't really do justice sort of what we've done. But once we did get the accurate outputs, we compared them with the OEM, which is the original equipment manufacturer of the F-35. And we had a percent difference no greater than 1.3%, which is accurate. And then we had some reactions that were even less than 0.03%. So we can say that with the outputs provided to us that this calculator is accurate as the OEM. So this is that scary math I was talking about. So to calculate the turnover angle, this is a sample calculation. Because it was in 3 dimensions, we really needed to like dive into those basic classes we took. So linear algebra, trigonometry, statics. I will save you all from going through the steps of how to do this. But I do have a sort of like a simulation to show what this math is doing. So we were given the jacking positions and the CG. And based on that, we derived all of these vectors, referenced each other, constrained them, and then constructed this triangle in 3D space. And here's the turnover angle. So then we use trigonometry to determine that angle between there, and that calculation happens every time that inputs are placed into the calculator, and they're accurate. So here we are at critical design. We have everything that you saw in the demo. We have the new bounds, which were added. We used another code that we wrote to iterate 5.3 million times to determine, okay, if the CG could happen anywhere across this aircraft, where is it stable? And then we plotted those points, and from there we constructed the red bounds that you see around there. And then they ended up as the dark blue and light turquoise bounds that you see on the calculator. So we did this not because we had to, but we wanted to further the sort of like the intuitiveness of like where stability happens, like geometrically, with respect to the weight of the aircraft. Now I'll pass it off to Bobby to handle our cost analysis.
Thank you, Grace. So first I'm gonna go over the cost or the estimated cost to manufacture our counterweights. So this is the cost to assemble or to manufacture and assemble a set of counterweights. So this would be the 2 that are on the aircraft over here on my right. So the material costs and purchase parts on the right-hand side on the screen came out to about $7,300. And the labor cost, this includes machining, welding, plating, anodize, painting, and the assembly. And this came out to an estimated cost of about $3,500. And total in those 2 together, the estimated cost to manufacture our steel counterweights assemblies was roughly $11,000, which in the grand scheme of things, that's relatively cheap and inexpensive to manufacture to solve this issue. Moving on, I'm gonna go over the non-recurring cost estimate. This is something for Capstone, we were to clock all of our time. So the hardware engineering and software engineering, that was the two different sub-teams. We clocked our hours. We worked on it individually outside of class. And then for group engineering, this was technical reviews and then group meetings that we had during class time. And this came out to about 1,750 hours that we worked on this Capstone project, which totaled about $273,000 of non-recurring engineering costs. And with that being said, I'm gonna open up the room to any questions on the project. Yes, ma'am.
Was any analysis performed to look at the weight? So they said they were 750 pounds. What does that do to the aircraft when they're placed on the wings?
Kind of like how Owens, when he went through the demo of the calculator, they kind of showed how, or are you saying like what it does to the actual structure of the aircraft?
Essentially damage the aircraft over time.
We were given, we talked to the customer early on in the project, and we were given a 1 PSI like maximum that we could, I guess, distribute over like the panels. And it would be like 864 pounds would hit that 1 PSI. And so we're under that 1 PSI that we were given. Are there any other questions?
Kind of have two. So the tipping angle, is that the point at which there's no more restoring moment is zero, or was there some fact? I saw something about a factor of safety in there. Or? So like, how did you decide what an acceptable tipping angle was?
So the basically like the wall, like the critical tip back angle was given to us by the customer. And from there we sort of like what was shown in the demo, we defined sort of bounds within that, like mini ones. So you know when it's getting really close, but once it hits like that 15 degrees and that 63 degrees, like that's it. So ideally we want to catch that before that so people can get off the aircraft and they can make it stable again or place the counterweights.
And you didn't have a variable counterweight, right? There wasn't like in some cases you're going to put 100 pounds of counterweight. It was always going to be 750 pounds.
Yes, sir.
Right now. We do have what was designed by hardware is just single-use counterweight. However, if they did decide that they want to create a variable counterweight, that functionality is supported by the software.
That was sort of two questions in one. My other question was more just to your process. So it was pretty clear that your first hardware concept very different from the final product. And the final product from our point of view right now looks sort of like the obvious solution, right? So I'm curious, what was it along the way that didn't make that obvious from the get-go?
We're kind of going through the project. There was kind of two conditions we were trying to achieve, right? Tip back and the turnover angle. Well, the turnover angle is the primary issue. So trying to solve both of those at once with one counterweight system was nearly impossible. I'm not going to say it's impossible, but nearly impossible, especially with the level of maintenance that's being performed on the aircraft and all over the aircraft. So trying to find a location where there's little to no maintenance being performed and somewhere we can place enough weight was definitely probably the most challenging part of the project, at least from a hardware perspective. And it is kind of interesting because you saw kind of there's a natural progression from we start off with this really complicated, cool, we're going to build all this extra structure and put it on the aircraft to we can go back and put two pieces on the aircraft that can be put on there in a couple minutes and solve the problem.
Don't forget that lesson.
Any other questions?
Was there any comparison between your final cost on this and in a commercial version from somewhere else? Another supplier?
I don't know if I can speak for software, but hardware, we didn't really like go quote it out per se to see. We really just looked at strictly what the material cost would be to be able to produce the counterweights as well as the engineering time that went into it, those non-recurring costs, which obviously you would not see again from the design perspective. If you were going to spec it out for someone else to manufacture, it would still just be pretty much the material costs and labor costs associated with that.
Daniel, am I correct? And there currently is not an available commercial solution. Someone would have to go and develop one just like you did.
Correct. Correct. With the counterweight and with the software, there's nothing quite like it.
Can you modify this for an Alpha and a Charlie, because they're going to have more than just Bravos going through FRC?
Yes. It would probably take a little more on the software side of things to be able to account for those two aircraft, because the jacking locations, which F-35 people can correct me if I'm wrong, are in different spots. The B model, this is particularly an issue because where this jack point is, there's the lift fan for the B model, and there's the engine. And it almost tries to teeter-totter over that nose landing gear, which is what's causing a lot of these turnover and tip-back conditions.
But I would say for software, with just some like intro knowledge on Python, since you import an Excel sheet, so you have a different Excel sheet with different parts and numbers for the different models, it could accommodate any Excel sheet if it's in the correct format. So you could pretty easily format it for different models if you wanted to.
Yeah, and you would also have to change the source code itself for the software, which the only thing you would have to change is the numbering for the wing jacks and the wing gear, like the center of gravity location for those, which is just an easy, quick number change as well.
Any other questions? All right. Well, we thank everyone